Hello my dear students, welcome back to my channel. This is the 7th lecture of Geometrical Optics. Till the last class, we started with refraction through plane surface. Today we will continue with refraction through plane surface and we will see image formation due to plane surface, right? Or you can say image formation due to refraction from plane surface. So let's begin with the class. We'll start with some questions and then we will derive the relation for the image formation by plane surface, right? Okay. In this question, it is given that find the angle theta A made by the light ray when it gets refracted from water to air, as shown in the figure. So it is given to you that this angle is sine inverse 3 by 5, right? And the light is traveling from water to air. You know by Snell's law, mu water sine theta water will be equal to mu air sine theta air. Now mu water is 4 by 3 and sine theta water is given as 3 by 5 is equal to mu air is 1 and sine theta A we need to find. So you will get sine theta A is equal to 4 by 5 or theta A is equal to sine inverse 4 by 5 and this can also be written as 53 degree. Okay. Then next question is find the speed of light in a medium A. We need to find the speed of light in a medium A if the speed of light in medium B is c by 3. Okay. So we need to find the speed of light in a medium A if the speed of light in medium B is c by 3 and it is given that c is the speed of light in vacuum and light refracts from medium A to medium B making an angle 45 degree and 60 degree. So that means light is traveling from medium A to medium B and it is making an angle here 45 degree and here 60 degree. Okay. Now you know that V mu1 sin I is equal to mu2 sin R and this can also be written as C2 sin I is equal to C1 sin R where C2 is the refractive index, the speed of light in medium 2. Now in medium 2 it is given that the speed of light is c by 3. So I'll write c by 3 into sin I, that is sin 45 degree, is equal to C1 we need to find, that is the speed of light in medium A we need to find, and the value of R is 60 degree. Okay, so from this you will get the value of C1 as C1 is equal to c by 3 root 2 into 2 by root 3 because sin 60 is root 3 by 2. So if I take it here it will become 2 by root 3. So you will get this is equal to root 2c by 3 root 3. Okay, so this is the value of the speed of light in medium A, right? Okay, then in the next question it is given that light of wavelength 600 nanometer enters from air to water. Okay, this is air to water. The water has refractive index 4 by 3. We need to find the speed, wavelength and frequency and color of light in water, right? So this is a very simple question. You know that refractive index is equal to C by Cm. This can also be written as lambda by lambda m, where lambda is wavelength in vacuum and lambda m is wavelength in medium. So lambda m is equal to lambda by mu. Okay. So first is find the speed of light in medium, right? That is speed of light in water. So speed of light in water will be how much? Speed of light in air or vacuum divided by mu. Now mu is 4 by 3, right? So I will write 3 into 10 raised to the power 8 divided by 4 by 3. So this will come out to be 9 by 4 into 10 raised to power 8, that is 2.25 into 10 raised to power 8 meter per second. Then wavelength is lambda by mu and that is equal to 600 or you can say 6000 angstrom divided by 4 by 3. So from this you will get 4500 angstrom. So the wavelength changes from 6000 angstrom to 4500 angstrom in the water. Okay. Then comes the color of light. Color depends on frequency and frequency is same. Okay, frequency does not change and frequency will be what? C is equal to lambda f. If you use C is equal to lambda f, C is 3 into 10 raised to power 8, lambda is 6000 angstrom. When you put the values of C and lambda, you will get the value of frequency as 5 into 10 raised to power 14 hertz. frequency does not change when light travels from one medium to other. That is why you will say that the color will remain the same. So 6000 angstrom is corresponding to yellow color. So you will say the color of light will still remain yellow when it moves from air to water. Okay. Then the next question is, a ray of light is incident on a transparent glass slab of refractive index 1.5. So it is given that the refractive index of the medium is 1.5. If the reflected rays and refracted rays are mutually perpendicular, then what is the angle of incidence? See what is given here. This is a incident ray and the reflected ray, but in this interface the light is not only getting reflected but also refracted. Okay, so this is the refracted ray. Okay, and suppose this angle is I, this angle will also be I, and this angle is R. Now it is given in the question that the reflected ray and the refracted ray are mutually perpendicular. That means this angle is 90 degree. Now this angle is I, so this is 90 minus I. This is R, so this is 90 minus R. Now according to question, 90 minus I plus 90 minus R is equal to 90. That means I plus R is equal to 90. That means I is equal to 90 minus R. That means sin I is equal to, or you can say cos I is equal to sin R. Cos I is equal to sin R. Now if you apply Snell's law here, you will get 1 into sin I, because the light is incident on a transparent glass slab. So this is the glass slab of refractive index 1.5 and this is air. Okay, so I will write 1 into sin I. 1 into sin I is equal to 1.5 into sin R, right? And sin R can be written as cos I, but sin I by cos I is tan I. So I will write tan I is equal to 1.5. So you will get I is equal to tan inverse mu. I is equal to tan inverse mu, where mu is 1.5. This angle of incidence, when the angle means the refracted ray and the reflected ray makes an angle 90 degree with each other, this particular angle of incidence at which that happens is called Brewster's angle. This is called Brewster's angle. This we will study in details when we study wave optics. In wave optics we will study Brewster's law in details. Okay, so whenever a light is getting reflected as well as refracted, if at one particular angle of incidence the angle between the refracted ray and the reflected ray becomes 90 degree, then that angle, which is equal to tan inverse mu, is called the Brewster's angle, right? Okay, then there are some questions for practice that you should do yourself. Okay, so take a pause in this and then try to solve it first, and then look for, then go for the remaining part of the video, right? Okay, now we will start with image formation by refraction through plane surface. So if there is a refraction through plane surface, we need to find the position of image. We will find the position of image only for near normal incidence. Okay, so we will do it in two cases. First is when the object is in a rarer medium, and the second is when the object is in a denser medium, right? Suppose the object is in a rarer medium. Okay, every time we will take the refractive index of the incident side as mu1. That means incident side means where the light ray, incident light is striking. Okay, that is the incident side, and the other side is the refracted side, and we will take the refractive index of the other side as mu2 every time, whether light is incident means moving from rarer to denser or denser to rarer, whatever. You will always take the incident side as mu1 and the refracted side as mu2. Okay, so I'll first show you what is this diagram. That is when the object is in the rarer medium. You know now that when light travels from a rarer medium to a denser medium, it bends towards the normal, right? So what I will do, I will draw two rays. First ray is perpendicular to the medium or the interface. You know that whenever light ray is perpendicular to the interface, in that case there is no deviation. Okay, so this is moving straight, right? Then there is the second light which is moving like this, and this eye is very small. I am drawing only for near normal incidence. That means the eye is looking from the top. The eye is looking from the top. The observer is exactly above the object. Okay, so that the angle here formed is very small. That is, I is nearly equal to 0 or very small, you can say. Okay, so you will say light ray will bend towards the normal, and this is the image formed. Why? Because this is the refracted ray, this is the refracted ray. It cannot intersect in this side, so the intersection side is this one, right? And it is virtually intersecting, so this image is a virtual image. That means when you look from the top, you will see that the object is not at this position but at this position. So this is image is actually called the apparent position of the object. This image is also called the apparent position of the object. I'll write here. Image is also called the apparent position of the object. Image is also called the apparent position of the object. Okay, so this image is also called the apparent position of the object. Now see, this is the object distance. Remember one thing, all distances will be measured from the interface. All distances will be measured from the interface. So if this is the object, this is the object distance, and this is the image formed, and this is the image distance. So whenever the object is in the rarer medium, di will be greater than do. Di will be greater than do. Okay. Now we will find the value or the relation between di and do. You have to learn this. So first let us derive it. So you know by Snell's law, you will write mu1 sine I, this angle is I, is equal to mu2 sine R, this angle is R. Okay. Now see, if this angle is R, this angle is also R, because these two are vertically opposite angles, right? Okay, then if this is R, this is also R. Why? Because these two are alternate angles. Similarly, if this is I, this whole angle is I, then this is I, because these two are alternate angles, right? Okay, now in this triangle you can see that I and R are very small. We are taking only near normal incidence. This is very important, for near normal incidence only. That means the angles will be very small. Okay, so you will say sine I here in this triangle, sine I is nearly equal to tan I is equal to PQ by OP, but OP is DO. Similarly, here you will write in this triangle sine R is nearly equal to tan R is equal to PQ by DI. Now you will divide it, you will get sine I by sine R is equal to PQ cancel, DI by DO. But from here Snell's law, sine I by sine R is mu2 by mu1. So from this you will get DI by DO is equal to mu2 by mu1, or you will say DI is equal to mu2 by mu1 into DO. You have to remember again, mu1 is incident side, mu2 is refracted side. Mu1 is incident side, mu2 is refracted side. Okay, again I am repeating, mu1 is incident side, mu2 is refracted side. This is the formula for finding the the position of the image. Di is equal to mu2 by mu1 into do. Sometimes di is also called the apparent position of the object. Sometimes this di is also called the apparent position of the object, because whenever the observer will look at this object, he will see that the object is not at this position but at this position. He will be unable to see the object at this position, but he will see the object at the position of the image. Okay, so this di is also called the apparent position of the object as seen by the observer, right? Now the next thing is, when the object is in the denser medium, that is the light is traveling from a denser to rarer. Light always originates from the object. Wherever there is the object, you have to draw the light from there only. Now let us look at this ray diagram. So here the light is traveling from a denser medium to a rarer medium, right? So that means the object is in denser medium. So this is the first ray which is perpendicular to the interface. You know that when the ray of light is perpendicular to the interface, there is no deviation and it moves in a straight line. Then this is the second ray, and when the light moves from a denser medium to a rarer medium, in that case the ray of light travels away from the normal, right? So this is away from the normal. These two rays cannot intersect here, it will intersect behind, right? So if it is intersecting behind, this is the point of intersection of these two rays, and this is the position of the image. So this length is di and this length is do, right? Again, the derivation is same. If this angle is r, this whole angle is r, and if this whole angle is r, this also angle is r. Why? Because these two are alternate angles. Similarly, if this angle is I, this angle is I. Again you will do the same thing. Mu1 sin I is equal to mu2 sin r, and sin I is nearly equal to tan I is equal to pq divided by do. Similarly, sin r is nearly equal to tan r is equal to pq divided by di. Again you will divide this two and you will get sin I by sin r is equal to di by do, but sin I by sin r is also equal to mu2 by mu1, and you will get the same formula, that is di is equal to mu2 by mu1 into do. Okay, so di again is also called the apparent position of the object. Di is also called the apparent position of the object. Now there is one important thing here that you should know, that both the formulas are same, right? Whether the object is in rarer medium or denser medium, the formula is same, and mu1 is the refractive index of the incident side and mu2 is the refractive index of the refracted side, right? And if the object is in denser medium, in that case di is less than do. Here see, di is less than do, and if the object is in rarer medium, di is greater than do. So if you are looking, generally you look from air, right? Generally you look from air. So that means the observer is in the rarer medium and the object is in the denser medium. This is the general case. Suppose a pencil is immersed in water. When you look from the top, you see that the pencil is shifted upwards. The pencil is shifted upwards. Okay, so that is the apparent position of the pencil that you are seeing. See, objects are appearing to shift upwards. So this observer is not seeing the object at this position, but he is seeing the object at this position, right? Okay, now suppose they ask you what is the velocity of the image. See, if you differentiate this with respect to time, then d di by dt is equal to mu2 by mu1 d do by dt. But d di by dt is what? D di by dt is the rate at which the position of the image is changing. The rate at which the position of image is changing with respect to the interface is called the velocity of image. Similarly, d do by dt is what? The rate at which the velocity, or you can say position of the object is changing. But the rate at which the position of the object is changing is called the velocity of the object. That means velocity of image is equal to mu2 by mu1 into velocity of object, right? And this velocity is with respect to the interface, because if interface moves, then also the distance is changing, because all distances are measured from the interface. So this velocity is with respect to the interface. Similarly, velocity of object is also with respect to the interface, right? Now some more important points are written here. First thing is, all distances are measured from the interface. I have told you. Second thing is, object and image always lie on the same side of the interface. See, object and image lie on the same side of the interface, right? If the object is upward, image is also upward. Object is downward, image is also downward. Okay, so these 2 points we have discussed. Then the third point is, this formula is valid even if the object is virtual. What do you mean by virtual object? Virtual object means a converging ray. Virtual object means a converging ray. What it means is, suppose a ray of light is coming like this, right? A ray of light is coming like this. In that case, it wants to intersect at this point. This is the position of virtual object. This is the position of virtual object. Okay. Now, here also you will say that the formula, that is di by do is equal to mu2 by mu1 is valid. Here you have to be very careful. See, it seems like the object is here, so you will say mu1 is this. No, mu1 is what? The refractive index of the incident side. Incident side is this only. Okay, although the object is behind this time because the object is virtual, but this is not mu1, this is mu1. Because this is the incident side. Mu1 is the refractive index of the medium of incident side, and mu2 is the refractive index of the medium of refracted side. Now I have drawn two rays here. Suppose this time the light is traveling from rarer to denser. If the light is traveling from rarer to denser, it will bend towards the normal, right? So it will bend towards the normal, and this will be the image. So if you look from this side, instead of here, you will see the image here. Okay, or you can say the object will appear to be here. If the light is traveling from a denser to a rarer medium. In that case, it will bend away from the normal, and this will be the position of the image that you will see. Okay, so this can be di if light is traveling from rarer to denser, and this can be di if light is traveling from rarer to denser to rarer. Okay, but both case formula is same. Di by do is equal to mu2 by mu1, where mu1 is the refractive index of incident side and mu2 is the refractive index of refracted side, right? Okay, I hope everybody has understood this by now. And sometimes they also ask you the shift in the position of the object. So the shift in the position of object is defined as do minus di, do minus di. Okay, and that is equal to do minus di can be written as mu2 by mu1 into do. So do into 1 minus mu2 by mu1. This is the shift in the position of the object due to this interface. That means although the object is present here, but actually apparently it feels like the object is here or here, depending on the values of the refractive index, right? Now let us do one question. In this question you have a bird and a fish. Okay, the distance given is 36 centimeter and 36 centimeter from the interface. This is the air water interface. The refractive index of air is n equal to 1 and the refractive index of water is n equal to 4 by 3. Then the question asked is, at what distance will bird appear to the fish and at what distance will fish appear to the bird? Okay, so first I will do case 1. At what distance will the bird appear to the fish? That means bird is the object and fish is the eye, or you can say fish is the observer. Bird is object and fish is observer. Bird is object and fish is observer. So if bird is object, then all distances are measured from the interface. So bird is object, that means I will write do is equal to 36. And you know that di is equal to mu2 by mu1 into do. And here you can see that light will travel from the object, right? So this is mu1 and this is mu2. Okay, that means light is traveling from air to water. So mu2 is 4 by 3. So I will write here this is equal to 4 by 3, mu1 is 1 and do is 36. From this you will get di is equal to 48. Okay, so di is equal to 48. So that means the fish will see the bird at this position, that is at a distance of 48 centimeter from the interface. So at what distance will the bird appear to the fish? Now fish is also at a distance 36 centimeter from the interface, right? So you will write 36 plus 48 centimeter. This is the answer. This is the distance between the bird and the fish as seen by the fish. Now in the second case what they are saying is, at what distance will the fish appear to the bird? So in this case the bird is the observer and fish is the object. So in this case we will write fish is the object. So if fish is the object, that means light is traveling from water to air. That means this time mu1 is 4 by 3 and mu2 is 1. And the formula remains same, that is di by do is equal to mu2 by mu1. Remember that this di and do are measured from the interface. Now this fish is the object, so do is 36. So again you will write di is equal to mu2 by mu1, that is 1 by 4 by 3, that is 3 by 4. Okay, multiplied by do is 36. So this time you will get 9 4 ja 36, 9 3 ja 27. So this time you will get di is equal to 27. So the distance between the bird and fish as seen by the bird will be, so this distance is 36 and this distance is how much? This distance is 27. Okay, although it is at a distance 36 actually, but bird will see the fish at a distance 27. So the distance between the bird and fish as seen by the bird is 36 plus 27. So the answer will be 36 plus 27. This is the distance between bird and fish as seen by the bird. Distance between bird and fish as seen by bird. Okay. Now the next thing is, see, if the bird is moving with a velocity of 1 centimeter per second. So this bird is moving downwards with a velocity of 1 centimeter per second. And the fish is moving upwards with a velocity of 3 centimeter per second. Then we need to find the velocity of bird as seen by fish. So again, in case question number 3, we need to find the, again I'll repeat, the velocity of bird as seen by fish. That means bird is the object and fish is the observer. So bird is the object and fish is the observer. Okay, so bird is the object and fish is the observer. So in this case, again let us draw the diagram. So this is the fish inside water and this is the bird, and bird is moving downwards with a speed of 1 centimeter per second. Okay, so velocity of image is equal to mu2 by mu1 into velocity of object, right? Now because bird is the object, the object, so this is mu1 and this is mu2, right? So mu1 is 1 and mu2 is 4 by 3. So I'll write velocity of image of bird is equal to mu2, that is 4 by 3, into velocity of object is 1. So that will be equal to minus 4 by 3 centimeter per second. Minus means downwards, right? So this is the velocity of the image of the bird. Now they are asked you what is the velocity of bird as seen by the fish. So velocity of bird with respect to fish will be equal to the velocity of image of bird, because fish is not seeing the bird, fish is actually seeing the image of the bird. So velocity of image of bird minus velocity of fish, because fish itself is also moving. Fish is moving upwards with 3 centimeter per second. So you will get the velocity of image of bird is minus 4 by 3 and velocity of fish is plus 3. So from this you will get 3, 3, 9, 9, 4, 13. So you will get minus 13 by 3 centimeter per second. This is the velocity of bird as seen by fish, right? Okay. Then there is velocity of fish as seen by bird. Okay, we need to find velocity of fish as seen by bird. So this time what will you say? This is fish, this is bird. So this time bird is the observer. This is the observer and fish is the object. Fish is the object. So this time what we will write? This time we will write velocity of image of fish. Why? Because fish is the object, is equal to mu2 by mu1. Now because this is the object, this is mu1, this is mu2, because light is traveling from here to here. Now mu1 is 4 by 3 and mu2 is 1. So mu2 by mu1, that is 3 by 4, into velocity of object is 3 centimeter per second upwards. So you will get 9 by 4 centimeter per second upwards. This is the velocity of the image of fish. Now they have asked you the velocity of fish as seen by the bird. That means you will write velocity of image of fish with respect to bird is equal to the velocity of image of fish minus velocity of bird. Now velocity of image of fish is 9 by 4 upwards and velocity of fish is 1 downwards, that means minus 1. So you will get 9, this is 13 by 4 centimeter per, right? So this is the answer. So velocity of fish as seen by the bird is 13 by 4 centimeter per second upwards, and velocity of bird as seen by fish is 13 by 3 centimeter per second downwards, right? So this is a very conceptual question. If you have not understood, then please again go through the video, again pause it and again try to solve it yourself, and then proceed to the next question. Let us now look at the next question. It is given to you that an object lies 100 centimeter inside water. So this is an object which lies 100 centimeter inside water and it is viewed normally, okay, from air. So this is air and this is water, that is mu is 4 by 3. Then find the apparent depth of the object. That means they have asked you di. You know that di by do, or you can write di is equal to mu2 by mu1 into do. Now because the object is in this medium, that means mu1 is this, mu2 is this. So you will write mu2 is 1, mu1 is 4 by 3. Okay, So you will write 3 by 4 is into 100, that is equal to 75 centimeter. This is the value of di. So this is the object and this is the image. This is 75 centimeter. Okay. Okay, then this is the image. Then let us look at the next question. In this question, it is given that an object lies 90 centimeter in air above the water surface. So this is the object which is above the water surface, 90 centimeter above the water surface. That means this is 1 and this is 4 by 3. It is viewed near normally. यहाँ से हम लोग देख रहे हैं, this is the viewing position. Okay, and find the apparent height of the object. Okay, so this time I will write again di is equal to mu2 by mu1 into do, but this time light is traveling from this medium to this medium. That means mu1 is 1, mu2 is 4 by 3. So mu2 is 4 by 3 and mu1 is 1 and do is 90. So from this you will get 120 centimeter. This is the apparent height of the object. Okay, then let us look at this question. In this question, it is given that there is a concave mirror here which is placed inside water. So this is water and a concave mirror is placed inside water with its shining surface upwards and the principal axis vertical. So this is the principal axis, right? Rays are incident parallel to the principal axis of a concave mirror. So this is the rays which are incident parallel to the principal axis of the concave mirror. Then we need to find the final position of the image. Now, because the rays are incidenting perpendicularly on the interface, that is why there will be no bending, that is why there will be no image. Okay, now this is the mirror, right? So basically what is happening here is the parallel beam of light which is parallel to the principal axis is striking the concave mirror. Okay, you know that when the parallel beam of light strikes the concave mirror, the image is formed at the focus. So here the image will be formed at the focus. So because the radius of curvature is 40 centimeter, you will say that the focus is 20 centimeter. Now if the focus is 20 centimeter, that means I will show you in this ray diagram itself, that means this is the image, right? This is the image. Now if the observer is watching from inside water, then this will be the answer. But if the observer is here, then what will he see? He will see that there is one more refraction that will go, means that this ray will undergo while reaching the eye of the observer. Okay, so due to this refraction there will be one more image and that will be the final image. So you will write again, this A is object for the interface. This A is object for the interface, right? So if this A is object for the interface, then you will use di by do is equal to mu2 by mu1. Now the light ray is going from this medium to this medium, that means this is mu1 and this is mu2. So mu1 is 4 by 3 and mu2 is 1. So this is equal to 1 by 4 by 3 and this is equal to di by do. Now distances are measured from the interface. So if this total length is 30 centimeter, this length is 20 centimeter, that means this length is 10 centimeter. So the object distance is 10 centimeter. So which implies, I will write like this, this is equal to di by 10 centimeter. From this you will get di is equal to 3 by 4 into 10, that is 7.5 centimeter from the interface. So the final image will be formed at this point where this is 7.5 centimeter from the interface. Now in the same question, let us modify this question. So let us modify this question and suppose that this is the concave mirror and this is the ray of light, means this is the water, and the ray of light again is perpendicular to the surface. Okay, the ray of light is perpendicular to the interface, but this distance is given as, suppose, 10 centimeter and the focus is 20 centimeter. So what will happen this time? This time if I draw the ray diagram, the image will be formed at focus, right? So the image is formed at focus, That means the image will be formed at this point. The image will be formed at this point from the mirror. The image will be formed at this point from the mirror, and I will draw this with a dotted line. Why? I am drawing this with a dotted line because the ray of light wanted to intersect at this point. This is the image, but because it has reached this interface, that is why you have to consider the refraction from this interface, and you have to see which is the final image from this interface. Okay, so this time this distance is how much? See, this total distance is 20, this distance is 10, so this distance is also 10 centimeter, right? Now if this distance is 10 centimeter, then you will again use di by do is equal to mu2 by mu1, and you have to be very careful here. This I1 acts as a virtual object. I1 acts as a virtual object. I1 acts as a virtual object for the concave mirror. For the concave mirror, I1 acts as a virtual not for the concave mirror, for the interface. I1 is the image of the concave mirror and it acts as a virtual object for the interface. Why virtual object? Because this is the interface and the ray of light here appears to intersect at this point. So this point is the virtual object for this interface, right? But you know that this formula is valid for both real and virtual object, right? So I'll write di is equal to mu2 by mu1 into du. You have to remember that mu1 is the refractive index of the incident side. Now light is, you have to see the ray of light. The ray of light is moving from this medium to this medium. If the ray of light is moving from this medium to this medium, that means this is the incident side and this is the refracted side, right? So I will write it like this. Mu1 is 4 by 3 and mu2 is 1. So I will write di is equal to mu2 is 1, mu1 is 4 by 3 and do is 10. So this will come out to be 7.5 centimeter from the interface. That means that it will bend like this and the final image will be this one. So this light wanted to meet here, but it will actually meet here. So this will be the final image. Okay, so this will be the final image I2, right? And this distance will be 7.5 centimeter from the interface. I have told you that object and image for an interface is always on the same side of the interface. See, this is the object and this is the image on the same side of the interface. If object is here, image cannot be here. Object and image will always lie on the same side of interface for a plane surface, right? Now let us look at one more question here. So actually this is the same question that we have discussed now. This is 10 centimeter. I have done this question now. This was 10 centimeter. Okay, so I have discussed this question and the final image position is 7.5 centimeter above the interface, right? Okay, then comes refraction through parallel slab. So if you have a parallel glass slab, in that case, when light ray pass from this medium, okay, and when it reaches this medium, these two rays are parallel provided the medium on both sides of the slab is same. Okay, so what I will read here, when light passes through a parallel slab having same medium on both sides, this is important, having same medium on both sides, then the emergent ray is parallel to the incident ray. The emergent ray is parallel to the incident ray, but it is laterally shifted. That means this is not collinear. These two lines are laterally shifted. That means these two lines are laterally shifted by a perpendicular distance d. So we need to find this d. This is called lateral displacement. This d is called lateral displacement, right? Okay. If the medium on both sides are different, in that case the rays will not be parallel. In fact, this is same as what we have discussed in the law of refraction, that if there are many transparent mediums which are parallel which have parallel interfaces, then two mediums which have same refractive index, in that two medium the rays are parallel. This is the same thing. If these two medium are same, then the rays will be parallel. Okay. Okay. then we need to find the value of this lateral displacement. Let us see. So when light is traveling from here, suppose this is a rarer medium, this is a denser medium, again this is a rarer medium. In that case, you will say that this is I, this is R, this one. Okay. And similarly here, if this is R, these two rays, these two are parallel lines and this is the transversal. So if this is R, this is also R, right? And if this is R, this will be I. Why? Because if you apply Snell's law here, you will say 1, that is N1 into sine I is equal to N2 into sine R. And if you apply here, you will say N2 into sine R is equal to N1 into sine I dash. This is I dash. From here you will see that these two are same. That means this two also has to be same. That means I has to be equal to I dash. So you will say I is equal to I dash. So this is again I dash is equal to I. Now suppose the thickness of the glass slab is T. So if this thickness is T and this is R, then from this triangle what will you say? From this triangle what will you say? See, I will draw it here. I will draw this triangle here. If this is T and this angle is R, I can clearly see that this is T sec R from the right angle triangle. So this length is T sec R. Okay. Then this angle is I, then this whole angle is I, right? And this is R, that means this angle is how much? This angle is I minus R. Now if you clearly look at this triangle, what will you see? You will see that this angle, sine of this angle is perpendicular by hypotenuse. Perpendicular is D, hypotenuse is T sec R, right? So I will write from here sine of I minus R is equal to sine of I minus R is equal to C. Perpendicular is D divided by this hypotenuse is T sec R. So we have got the value of lateral displacement and that is equal to T sec R sine I minus R. You can also remember this as D is equal to T sine I minus R divided by cos R. Why? Because sec R can be written as 1 by cos R, right? So this is the value of lateral displacement. So again I will repeat, whenever a ray of light passes through a glass slab and the medium on both sides of the slab is same, normally it is air, then the emergent ray is parallel to the incident ray, but it is laterally shifted and that lateral displacement value is equal to T sine I minus R by cos R. Okay, and I and R relation is found out using this relation. I and R relation is found out using this equation. Okay, so this is the lateral shift. Now one lateral shift is one thing, then there is also apparent shift in the position of the object due to a glass slab. You know that if there is one interface, then due to this interface, suppose this is the position of the object, but when you look at this object from this this position, what will you see? You will not see the object in this position, but you will see the object at some shifted position, right? So for this observer, the object is actually here. Although actually the object is here, but this observer sees the object to be here, right? So from one interface, the image you can say is shifted, right? This is called apparent shift. Similarly, if there are two interfaces, then also there will be shift, right? So we need to find the shift in image due to a glass slab. That means what we need to find is, if this is the glass slab and this is the position of object and you are watching it from here, then at what position you will find the image. Okay, so suppose this is the object, this is the image. That means when this observer was looking through the glass slab, although position of object was this, but he was getting the position as this. This is because of the glass slab. That is called the apparent shift. So we need to find the apparent shift for a glass slab, just like we found out for a one interface. Okay, now we have two interfaces. Okay, let us see. So before that, let us do one simple question of lateral displacement. Find the lateral shift of light ray, which while it passes through a parallel slab of thickness, it is given as 10 centimeter, and the angle of incidence is 60 degree and the angle of refraction is 45 degree. So they have given you I, they have given you R, you know the formula for lateral displacement. Okay, you can find it yourself. Okay, there is one more question here. A ray of light falls at an angle of 30 degree onto a plane parallel glass plate and leaves it parallel to the initial ray. So it is given to you that there is a glass plate and a ray of light falls at an angle of 30 degree and leaves it parallel to the initial ray. Obviously, this is a glass slab, so the final ray will be parallel to the initial ray. The refractive index of the glass slab is given as 1.5. Then what is the thickness of glass plate if the distance between the rays, that is the lateral displacement, is 3.82? So clearly you will say 3.82 is equal to T sine I minus R divided by sec R. Okay, and the value of T is given as, or value of T, this is written as T. The value of T is given as, so value of T they have not given. In fact, they have asked you the value of what is the thickness of the plate. Okay, so they have asked you the value of T. So they have given you I and R. How? You will use this relation, 1 into sine 30 is equal to 1.5 into sine R. So from this you will get the value of R. And once you get the value of R, you will put it here and you will get the answer. Okay. Sorry, this was not sec R, it was cos R. Right. Okay. So from this you can use the given data. Okay. Now, apparent shift, this was what I was talking about. Now, apparent shift, listen carefully. We will discuss it in two cases. One is for a converging rays. For converging rays means the object is virtual, and the other is for diverging rays. For diverging rays, that means the object is real. So this is the diverging ray. This is the diverging ray, that is the object is real, and here I am discussing the converging ray, that means the object is virtual. Okay, everybody now listen carefully. Suppose the medium on both sides of the slab is same and the refractive index is 1. That means the medium on both sides of the slab is air. Okay, and the refractive index of the glass slab is mu. Right? Okay, so this is the converging ray and it wanted to converge at this point O. So this is the position of the object. Right? This is the first interface. This is the first interface and this is the second interface. Okay, so this is the first interface and this is the second interface. Now let the distance of the object from the first interface be DO, right, and the distance of the image formed from the first interface be DI1. Okay, so in that case what will you say? This is the formula I have written first. I will discuss the formula also. First let us derive it, right? So here for the first surface what we will write? Di by do is equal to mu2 by mu1. Now di is how much? Di is di1. Do is this one, do is equal to mu2 by mu1. Now light is traveling from this to this. So that is, this is the incident side. This is mu1, this is mu2, right? So I will write mu2 is mu. So I will write here mu2 is mu by 1. So from this you get di1 is equal to mu do. Now once you get the value of di1 which is equal to mu times do, that means what? See, di1 is greater than do. Okay, so because here light is traveling from a rarer to denser medium, so that is why it is bending towards the normal. So if it is bending towards the normal, that is why the image formed is here. So that is the image from the first interface, right? This ray wanted to intersect at this point, but again second interface came. Okay, so that means I1 acts as object for the second interface. I1 acts as a virtual object, for the second interface. For the second interface, I1 acts as virtual object for the second interface. So for the second interface, this is the object distance, right? And suppose the image formed is at this point, so this is the image distance. right? This is object distance and this is image distance, right? Okay then. So from the first interface, let the image of I2 be di2. This is from the first interface. Okay. Now listen carefully. For the second interface, again you know that di by do has to be equal to mu2 by mu1, and this time the ray of light is traveling from this medium to this medium. Now if the ray of light is traveling from this medium to this medium, that means this is the incident side and this is the refracted side. Now if this is the incident side, that means the refractive index mu1 is mu and the refractive index mu2 is 1. So this time I will write mu2 by mu1 is 1 by mu. Okay. So here I have written di by do is equal to 1 by mu for the second surface. Now listen carefully. For the second surface, what is the object distance? So I1 was object. Now this whole distance is di1, and suppose T is the thickness of the glass slab. T is the thickness of the glass slab. So that means the object distance from the second interface will be di1 minus T. So here see, here we have written di1 minus T is the object distance. Then the image formed is where? The image formed is here. Okay, image formed is here. That is why I will write the image distance is T. This distance from the first interface is di2 and this thickness is T. That means this distance, that is the image distance, is how much? The image distance is di2 minus T. Okay, because we need this distance, because all distances are measured for the interface. All distances are measured from the interface. Whenever you use formula di by do is equal to mu2 by mu1, right? So here we will say that the image distance is di2 minus T. So I have written it here. See, di is di2 minus T. So you will get di2 minus T divided by di1 minus T is equal to 1 by mu, right? Now when you solve this, you will get di2 is equal to T plus di1 minus T divided by mu, and di1 was, see from here, di1 was mu do. So here I will write di1 is mu do. So you will get T plus mu do by mu minus T by mu, that is equal to T plus mu cancel do minus T by mu, right? Now what is the shift? What is the shift? The shift will be di2 minus, listen carefully, this distance is do, this distance is do, this distance is di2. So this is the shift. Shift is always calculated from the final image, because when you look from this side, you will look at the image at this point only. You will not see the object, you will not see this image, you will see this only, right? Okay. So what we were discussing is that I2 is the final position of the image, and you will be seeing this position, this image only. Okay, and the shift will be equal to di2. The shift will be equal to how much? di2 minus do. Okay, again I will say di2 is this distance. Listen carefully. di2 is this distance, do is this distance, and this distance is the shift, or you can say this is the apparent shift. Okay, so the apparent shift will be equal to di2 minus do, but di2 we have calculated T plus do minus T by mu, and do is what? Do, let us remain it do only. So you will get do getting cancelled out, you will get T into 1 minus 1 by mu. So this is the formula for shift, and this is a very, very important formula. You have to learn it. Whenever there is a glass slab, the shift in the position of object, or you can say the apparent shift in the position of object, is given by T into 1 minus 1 by mu. Now in this derivation, what we have done is we have taken this medium on both sides has refractive index 1. But if the medium has refractive index, suppose mu dash, if the medium on both sides is same, but the medium has refractive index mu dash instead of 1, then the shift will be given by T into 1 minus 1 by mu relative. where mu relative is equal to the mu of the glass slab divided by the mu of the medium, right? Previously it was 1, that is why the formula was T into 1 minus 1 by mu. Now it is mu by mu dash, because the medium is not 1 but mu dash. Okay, so if on both sides of the slab there is same medium but that medium has refractive index mu dash, in that case the formula will become T into 1 minus 1 by mu relative. Now what is the importance of this formula? What are the important points regarding this formula? We will discuss that, but before that we will also derive it for a converging ray. Okay, sorry, for a diverging ray. Sorry. Okay, so diverging ray, listen carefully. Suppose this is the object. So this time the object is real because the rays are diverging and rays diverge from the point of real object. So this is the real object. Okay, you know that when there is a ray which is perpendicular to the surface, it does not deviate, okay, or it does not refract, it moves in a straight line. So this ray I have drawn in a straight line, and this ray, light is moving from rarer medium to denser medium, so it is bending towards the normal, right? So this is the position of image from the first interface. This is the position of image from the first interface. So for the first interface I will use di by do is equal to mu2 by mu1. So you will get di1 is equal to mu do. So that is, this is di1 and this is do, and di1 is equal to mu do. Now for the second interface, this is the second interface. Second interface, what is happening is it feels like there is a ray of light on the second interface which is coming from this point. That means I1 acts as object for second interface. I1 acts as object for second interface. Now if I1 is object for the second interface, that means what? See, if I1 is object for the second interface, then the object distance becomes di1 plus t. The object distance becomes di1 plus t. And suppose the image is formed here. Why the image is formed here? I am drawing the ray diagram. See, light is now traveling from denser to rarer medium. If light travels from denser to rarer medium, it bends away from the normal. If this is bending away from the normal, in that case, what will you do? See, this is the bending away from the normal, and this is the ray. This means this ray is perpendicular to this interface, right? So that is why it is not bending. Now these two rays cannot intersect this side, but it is intersecting behind. So the intersection point is this one. So this is the image. Okay, so this is the image. Now this distance is di2, right? So I can write di2, I have written here from the first interface. Then I will write the image distance for this interface is di2 plus t. Okay, so here di by do is mu2 by mu1, where di can be written as, listen carefully, di can be written as di2 plus t. Okay, and similarly do can be written as, now I1 is the object for this, so do can be written as di1 plus t is equal to mu2 by mu1. Now light ray this time is traveling from here to here. So this is mu1, this is mu2. So mu2 is 1, mu1 is mu. So I will write 1 by mu. Okay, so when you solve this, you will get di2 is equal to di1 plus t by mu minus t. Okay, so di1 can be written as mu times do. From the first interface, di1 is equal to mu times do, right? So mu do plus t by mu minus t, that is equal to do, mu cancel, plus t by mu minus t. Now the apparent shift, see, this distance is called the apparent shift, the distance between the object and the image. The distance between the object and the image is called apparent shift, right? The apparent shift will be do minus di2. Okay, so if I do do minus di2, I will get do minus di2 is equal to t into 1 minus 1 by mu. You get the same formula. Again, if medium on both sides of the slab is not air, but some other medium, say mu dash, then the shift will be t into 1 minus 1 by mu relative, where mu relative is mu by mu dash, where mu dash is the refractive index of the medium and mu is the refractive index, right? So some important points about this formula. Okay, I will write it again. See, this is some important points about this formula. You have to remember this formula. This is very, very important. Some important points about this formula. Okay, the first important point, that is shift is same. Shift is same. Formula of shift is same whether the ray is convergent or divergent. Okay, so this is something that I have already told you, right? Then the next point is also very, 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 very important. Shift is independent of the position of object, slab, or the observer. Listen carefully, what does this mean? Suppose this is the slab and this is the object and this is the observer, right? Now suppose the object is shifted here. Okay, so whether the object is here, here, whatever be the position of the object, whatever be the distance of the object from the slab, shift will remain same. Look carefully, the formula of shift, T into 1 minus 1 by mu. Shift depends only on the thickness of the slab and the refractive index or the relative refractive index of the slab with respect to the medium. Shift does not depend on the position of the object or the position of the slab or the position of the observer. So if you shift the slab here, then also the shift in image will be same. If you shift the slab here, then also this observer will see the shift in the position of object as same. Apparent shift, what we call. Okay, so shift is independent of the position of the object, slab, and the observer. Then this is also very, very important. This shift can be positive or negative. This shift can be positive or negative. Normally it is positive only because mu relative is greater than 1. Okay, but sometimes it might happen that this mu relative becomes less than 1, because mu by mu dash can become less than 1 when mu dash is more. Okay, so if mu dash is more, then mu by mu dash becomes less than 1. Then 1 by mu dash will become more than 1. That means it will become negative, right? For air it will be positive only. For glass slab and air it will be positive only, but for any other medium it might come out to be negative. So shift can be positive or negative. Shift can be positive or negative, but it is mostly positive. In normal situation it will be positive, but in exceptional situation it might come out to be negative also, right? Now if the shift is positive, listen carefully, if the shift is positive, the shift will always be in the direction of incident ray. If you look at the diagram for the convergent ray first, then assuming that the shift is positive, then it was about to intersect here, but it will intersect here. See, the shift is positive, that means it will be in the direction of incident ray. So if the incident ray is towards right, the shift is towards right. Similarly, if you look for a divergent ray, that means a real object, in that case what will happen? In that case, you know that the shift is again towards right. I will show you the diagram again. See, I will show you the diagram again here. See, this was the object and this was the final image. Shift was towards right. Why? Because the incident ray is towards. So shift is always in the direction of incident ray if it is positive, and if it is negative, it is opposite to the direction of incident. So this is very, very important. Shift is in the direction of incident ray if the shift is positive, and opposite to the direction of incident ray if the shift is negative. Okay, then formula is same that I have already discussed, and this formula is valid only if the medium of object and observer is same. That I have already told you. The medium on both sides of the slab has to be same. The medium on both sides of the slab has to be same. Whether it is air or any other medium, that is a different thing, but it has to be same. Only then you can apply the formula for shift, right? Okay, then if there are multiple number of slabs, you have to remember this. Again I will repeat, formula for shift is very, 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 very important. Also the important points, that the note that I have given you, that is also very, very important. You have to read it again. If you want, you can take a pause here, read it again, write the notes, and then move to the next part of the video, right? Then you have multiple slabs. If you have multiple slabs, then there is a general formula. Okay. So suppose this is the object and this is the combination of slabs, and here the medium is mu dash, here also the medium is mu dash. Again, the medium on both side of the means the medium of the object and the medium of the observer has to be same for the formula to be applicable. Okay. Now again they are asking what is the shift in the position of object. The shift in the position of object is given by the sum of shifts due to all the slabs, right? Okay, listen carefully. Sum of shifts due to all the slabs. So you will write T1 into 1 minus 1 by mu1 relative plus T2 into 1 minus 1 by mu2 relative plus T3 into 1 minus 1 by mu3 relative plus T4 into 1 minus 1 by mu4 relative. Now relative to what? Relative to the medium of the observer or the object. Both has to be in the same means you can say same medium. Okay. So you will say mu1 relative is mu1 by mu dash, mu2 relative will be mu2 by mu dash, mu3 relative will be mu3 by mu dash, mu4 relative will be mu4 by mu dash. Again the shift will be independent of the position of object. It can be here, it can be here, it can be here. Similarly it is independent of the position of the observer, that means it can be here, it can be here. Okay. Similarly it can be independent of the position of the slab, that means the slab can be here. Okay. So the shift is independent of the position of the slab, the object and the observer. It depends only on the thickness of the individual slabs, right? Okay. So basically you have to do sum of the shifts due to all the slabs, right? Now listen one thing carefully. When you write here mu2 relative, do not write mu2 with respect to mu1. No. Everything you have to write with respect to the medium of the observer. Everything you have to write with respect to the medium of the observer. Okay. Okay, then there is one more formula that we can write, that is, listen carefully. Suppose I will draw one more diagram here so that this is clear. Suppose you have some mediums mu1, mu2, mu3, mu4, and this distance is T1, T2, T3, T4. Okay, and this is the observer and this is the object. Okay, and suppose this distance is T. Then what is the object distance from the last interface? What is the object distance from the last interface? Listen carefully. What is the object distance from the last interface? It is T plus T1 plus T2 plus T3 plus T4, right? And what is the image distance from the last interface? The image distance from the last interface will be, listen carefully now, T by mu, suppose this refractive index is mu dash, then I will write T by mu dash relative plus T1 by mu1 relative plus T2 by mu2 relative plus T3 by mu3 relative plus dot dot dot. Okay. Now suppose the refractive index of the medium of the observer is mu double dash, then mu dash relative will be the refractive index of this medium with respect to the medium of the observer. This time what I have done is I have taken the medium of the object and the medium of the observer different. Okay. So that is why this time I will write mu dash relative is equal to mu dash divided by the mu of the observer, that is equal to mu double dash. Similarly, mu1 relative will be the refractive index of medium 1 with respect to the medium of the observer, that is mu1 by mu double dash. Similarly, refractive index of 2 relative will be equal to mu2 by mu double dash. Okay. Now if these two are same, in that case write mu dash is equal to mu double dash, then this will become 1. Okay. Now there is a term called equivalent refractive index. Equivalent refractive index. Okay. Now listen carefully first. This is the formula. Object distance you can directly see, but the image distance from the last interface, listen carefully. This image distance that we have learned here, this is the formula, you have to remember it. This image distance from the last interface, this distance is from the last interface. Okay. So here again I will repeat, there is a term called equivalent refractive index, and equivalent refractive index is equal to apparent distance, or sorry, actual distance by apparent distance. Actual distance by apparent distance. This is called the equivalent refractive index. That is T plus T1 plus T2 plus T3 plus T4 divided by T by mu1 relative, mu dash relative plus T1 by mu1 relative plus T2 by mu2 relative plus dot dot so on. Okay. Let us look at one simple question here, and this is very important. Suppose you have three mediums like this. Okay, three liquids, you have three liquids, right? And the refractive index is given to you as mu1, mu2 and mu3, and this is air. This is the observer, and here there is the object, right? So this distance is given as d1, d2, d3. So obviously you can see if this is the object, this is the last interface. This is the last interface. All distance we will measure from the last interface. So DO will be how much? DO will be D1 plus D2 plus D3. DI will be how much? DI will be, so formula, remember the formula, D1 by, so actually let us say this is mu1, this is mu1, mu2, mu3, so that there is no confusion. See, Di will be equal to D1 by mu1 relative. Now mu1 relative is mu1 by 1 only because this is air, plus D2 by mu2 relative plus D3 by mu3 relative. Okay, because this object is here only in this medium, so there is this distance is 0. Okay, so it is here only, right? So Di by DO is mu equivalent. Mu equivalent is Di by DO, and that will be equal to D1 by mu1 plus D2 by mu2 plus D3 by mu3 divided by D1 plus D2 plus D3. Okay. Now they can also ask you this question like this. Listen carefully. Find the image of the base. Find the image of the base as seen by the observer. As seen by the observer. So the image of the base as seen by the observer is again the same answer. D1 by mu1 plus D2 by mu2 plus D3 by mu3, because the base is the object. Okay. Now there is one more important question that can be asked here. Listen carefully. Suppose this is a liquid of refractive index, say mu1, right, or mu, and this is the observer, right? Now the observer finds the container to be half filled, finds the container to be half filled. So suppose this height is h, then how much is the actual height of the water or the liquid? What is the actual height of the liquid? That is h dash. What is the actual height of the liquid? Okay, so this is the base, but actually, listen carefully, this is the base, but actually this observer is not seeing the base at this position. Observer is seeing the base at some lifted position. Okay, and what will be that position? That will be equal to, you know, that Di is equal to h dash divided by mu, because there is only one liquid. If there was more than one liquid, then D1 by mu1 plus D2 by mu2 plus D3 by mu3. Here, because there is only one liquid, so I will write Di is equal to h dash by mu. So the base apparently is at this position according to the observer, right? Okay, then he finds the container to be half filled. That means what? Listen carefully. So here you can say that, see, if this is half filled or this appears to be half filled, in that case this is what? See, suppose you have filled it with h dash. So this distance will be how much? H minus h dash. And apparently it looks like this distance is h dash by mu. Now if this is half filled or this appears to be half filled, then this and this has to be same. So that means h minus h dash has to be equal to h dash by mu. So from this you will get h dash common 1 plus 1 by mu is equal to h. So from this you will get h dash is equal to h mu divided by mu plus 1. So this is the height up to which you will fill the liquid, or means you will fill the container so that it appears to be half filled when you see it from the top, right? With this we have come to the end of today's class. In the next class we will be discussing some more problems related to refraction through plane surface and image formation through plane surface. Till then, bye bye, and if you like my video, please like, share and subscribe my channel.